Hello everyone, this is the third lecture of this week. We have been discussing the various steps involved in analysis of beams through matrix method of structural analysis. And if you recall, these are the different methods, these are the different steps involved in matrix method of structural analysis, and these steps we demonstrated in the context of truss problem. Same thing we have been doing for beam. Now, we already discussed what is how to discretize a beam and how to give the numbering. We also discussed what is the stiffness matrix for different members, and then we discussed how to assemble these stiffness matrices to get the global stiffness matrix. Today, we will see how to apply the boundary conditions and then how to construct the load vector. That is today's topic. Okay. Okay, and rest of the solution of these solution of the system of linear equations and then determination of support reactions, we won't discuss the steps. We will demonstrate directly through an example in the subsequent classes. Okay, so if you recall, this is the problem we have chosen to demonstrate the steps, and remember, one thing is very important when we our objective here to demonstrate this step. That is why let us not right now bother about how to number different members, how to number different degrees of freedom. We will discuss that when we actually demonstrate these steps, when we actually find out the solution of that problem. Okay. So, we have seen this global stiffness matrix of this beam is like this. It is a 6 by 6 matrix because we have total 6 degrees of freedom. Now, so this is how we have given the numbering of the degrees of freedom, but again let me repeat that once again. This is not always you have to choose the numbering like this. Like we have given node number 1, the degrees of freedom is U1, U2, node number 2 it is U3, U4, and node number 3 it is U5, U6. You can have U1, U2 for node number 2, you can have say U3, U6 at node number 1 and so on. So, how depending on the structure, depending on the unknown displacement, unknown degrees of freedom, how to give this numbering, that we will discuss when we actually find out the solution. But here our objective is not to discuss the numbering part. Here our objective is to understand various steps involved in this analysis method. Okay. So, for instance, if you have to the bound, these are the displacement and these are the load vectors, and these displacement and the load vectors are related to each other through this example, through this equation, where K is the stiffness matrix, is the global stiffness matrix, and then this is the global stiffness matrix, and P is the load vector, global load vector, 6 components, and U is the global displacement. This. Now, next what we do is, if you try to find out the if you try to inverse this stiffness matrix, you will see this is not invertible. This matrix is singular matrix, and the physical manifestation of that singular matrix, that is the structure is not stable. Structure is not stable because we have not provided sufficient constraint to the structure, sufficient support to the structure. And now we have to, once we provide the sufficient support to the structure becomes stable, but that information has to be translated in this equation, and that information need to be translated in this equation through applying the boundary conditions. Now, what are the boundary conditions we have here? For instance, in this case, if we take, in this case, we have all U1, U2, this is a fixed end. So, this is straight, this is 0. So, this is, take different color. So, this is 0, then this is also 0, and then U3 in this case this is 0, and then U5 is also 0. So, only unknown displacements in this case U4 and U5. If you number it like this, then U4 and U5 are the unknown displacement, and U1, U2, U3 and U6 all are known displacement, means they are 0 displacement. You may not have always 0 displacement. You can suppose in the case of support settlement, you know how much support is settled. So, if you know the displacement, some known value of displacement you are providing to the structure, then U6 may not be 0, then U may not be 0 at that point, U may be the specified displacement at that point. But in this case, the that displacement is 0. So, that is the boundary condition. Okay. Now, once we have the boundary conditions, let us see how to construct the load vector. So, this is the boundary condition we already discussed. Let us see now nodal load vector. In order to calculate the nodal load vector, we have to recall some of the things that we discussed that you have already learned in your structural analysis 1, analysis of indeterminate structure using displacement method, specifically slope deflection method. And there you let us that information, that concept is required to construct the load vector. Let us recall that. Suppose you have a structure like this, and then what we did in displacement method, first we assume all these degrees of freedoms are constrained. Okay, there is no degrees of freedom in this structure. So, we make this structure kinematically determinate. So, this is the structure which is kinematically determinate with external load. Okay. Then what we did is we had taken the each segment separately. Suppose this segment separately we took. Now, all these beams separately, now they all are fixed beam. So, they are fixed beam and subjected to the external load. Okay. Then we can then solve this using any method. We can solve this fixed beam separately, and we can find out the moments at this support, and those moments are called fixed end moments. Okay. Now, so these moments are the fixed end moments. Similarly, if you calculate the moments for BC, this will be the fixed end moments. As per our sign convention, anti-clockwise rotation and anti-clockwise moment are considered as positive. That is why in these fixed end moments, the anti-clockwise directions are shown as positive. Okay. Similarly, you can have moments here. You can have, these are all fixed end moments. So, MAB is the fixed end moments in AB at end A. Similarly, FBA is the fixed end moment in segment BA at point B. Similarly, MD is the fixed end moment in D at point D. F stands for fixed end moments. Similarly, you can have fixed end reactions. Reactions means in this case the vertical forces. These are the vertical forces. So, these are called fixed end moments and these are called fixed end forces, and together this M and R, they are called fixed end actions. Now, once we have the fixed end actions, what you did in the displacement method. Now, the next, if you recall, so this is a primary structure with external loading. Primary structures are statically, kinematically determinate structure. All the degrees of freedoms are constrained. But then in actual structure, it deforms, right? And suppose this structure deforms like this. Okay. So, in these cases, in all these cases, you assume that theta b is equal to 0, then theta c is equal to 0, theta d is equal to 0, and so on. But then in actual structure, we cannot have theta b, theta c, theta d, theta e, they are is equal to 0. They have some non-zero values. Okay. Now, if you assume that this red line is the deformed shape of this structure, where you allow the deformation, you allow these degrees of freedom. Okay. Then this is called, this structure is called primary structure with redundant. Now, then what you did is, then now in order to get this deformation, this red deformation shape, you need certain forces, right? But this structure there is no force. All the forces are with all the external load is only on the primary structure. Now, in order to create this deformation, what you have to do is you have to apply some force, right? Say for instance, you have to apply some force. And then some force like this. Some forces like this. Okay. Then the equivalent joint load. See, in the case of in case of truss, what happened is we always apply load at the joints, right? We don't apply load on the members because that is how the truss needs to be idealized. But then in the case of beam, we not only have force on the joint, we can have also force on the member. But when you solve equation ku is equal to f, p is equal to ku, that equation is defined at the node. You get the nodal displacements, and therefore you need the load that is specified at the node. Therefore, all the member load needs to be translated at the only projected at the node, and this projected load is called the equivalent joint load. Why it is called equivalent joint load? Because whatever effect you have, that effect should be same. Effect should be same means the structure subjected to the external load, the way the structure deform, the equivalent joint load gives you the same amount of deformation at the joint. That is why it is called equivalent joint load, but in this case the forces are applied at the joint, and suppose these are called the equivalent joint load. Okay. Now, the equivalent joint load, since their effect will be same, then it says that the equilibrium, these forces and this fixed end reaction should equilibrate each other. That is how you did in displacement method, slope deflection method. So, if they have to equilibrate each other, then suppose this is P1, this is P1, this is P2, and this is P3, and this is P4, then equilibrium says that P1 plus R B A F plus R BCF, that is equal to 0, and this gives you P1 is equal to minus R BF plus R BC, F fix. Okay. So, this is equivalent joint force at node number 1. Similarly, if you moment equilibrium, if you satisfy, then the moment equilibrium will be P2 plus, then we have anticlockwise moment MBAF plus, then we have MBCF, that is equal to 0, and this gives you P2 is equal to minus MBA plus MBCF. So, this is the equivalent joint load at equivalent joint moment at 2. So, P1 and P2 are the equivalent joint load at node number B. Similarly, if you satisfy the equilibrium at every joint, we get the corresponding equivalent joint load. But remember, these equivalent joint loads are not the support reactions. Support reactions are the equivalent joint load whatever you have, plus the because of this deformation there will be some contribution to the reactions, and the total reaction, that reaction will be the effect of deformation plus this fixed end actions. Okay. Now, next is, so this is how we construct the equivalent joint load, right. Now, probably if you still have some confusion when you actually demonstrate them through an example, this confusion will be clear. So, we discussed that what is equivalent joint load. Now, once we have the equivalent joint load for this problem, say P1, P, these are the equivalent joint loads and they are the support displacement, then we have, and this is how this load vector and displacements are related to each other. Okay. Now, then you see this entire thing, this entire load vector in this case can be rearranged in such a way that all the known displacements are kept one side and all the unknown displacements are kept one side. For instance, here in this case, these are all unknown displacement and these are all known displacement. Suppose this is written as u unknown and this is written as u known displacement. Okay. Then what we can do is, So these are all known, these are all unknown displacement, and these are all known displacement. Okay. Now, so your force displacement relation was initially like this. Now, if you rearrange them, taking all the unknown displacement at one side and the known displacement at another side, I mean together, then this rearrangement will be something like this. So these are all known, unknown. So these are our unknown displacement. This side all unknown displacement and on displacement. When you rearrange this load vector and then displacement vector, corresponding rearrangement needs to be done in the stiffness matrix, and this exercise is called partitioning of the stiffness matrix. It is to be partitioned in such a way that known displacement and unknown displacements are taken separately. Okay. Now once we partition the stiffness matrix, now look at this stiffness matrix, look at this expression. From this expression we can write just from this, the first equation if we write, then this equation become this. Okay. Now this is, in this case this is 0, so entire part becomes 0. K11 is this part of this stiffness matrix. P4, P6 are the corresponding nodal joint, equivalent joint load. These and these we already know how to determine them, and then if we solve them, then we get U4 and U6. Now once we solve it for U4 and U6, then U1, U2, U3, all other this is U5, all other displacements at 0. So we have information about the all displacements. Once we have the information about all the displacement, the next step is to find out the support reactions and then other information about the beam, behavior of the beam that we are interested in. So but that exercise, how to find out support reactions and how to find out support reactions from this, and then how to find out other information about the behavior of the beam, we will not discuss through steps. Let us start an example in the next class and demonstrate all the steps that we discuss in first three classes, and some of the confusion if you still have, I believe that those confusion will be clear when we see some example. So we'll have two example in this course. One example is the same example we will consider in the next class, and then we will find out the solution of this example, and then we will have one more example in the subsequent classes. Okay, I stop here today. See you in the next class. Thank you.